In this lecture, we're going to develop the idea of the law of chemical equilibrium, and we're going to define the equilibrium constant. So, the law of chemical equilibrium states that at a given temperature, a chemical system, or reaction, reaches a state at which the ratio of reactant and product concentrations raised to the powers of their respective stoichiometric coefficients is constant. So, just on reading that, that probably doesn't make a whole lot of sense. So I want to develop an example and define the equilibrium constant, which is this ratio of products to reactants, in detail. Let's take as our example a reaction where we have carbon dioxide decomposing to carbon monoxide and oxygen. So 2CO2 decomposing to 2CO plus O2. Okay, this is an equilibrium reaction, so I've written it with equilibrium arrows in the forward and reverse directions. Now, suppose you started with a concentration of 0.250 molar CO2 and you ended with a concentration of 0.040 molar carbon monoxide, CO. From that information, can you figure out the final O2 and CO2 concentrations? Okay, so we should be able to do this. Just thinking back even to what we learned a long time ago about stoichiometry. So I would like you to note, just looking at the stoichiometry of the reaction, that there are going to be 2 moles of CO produced for every 1 mole of oxygen, right? You can see that from the molar ratio of those stoichiometric coefficients. So there are 2 moles of CO produced for every 1 mole of oxygen. So that means that if we produce at equilibrium, let's say, if the carbon monoxide concentration is going to be 0.040 molar, that means that the O2 concentration is going to be half of that. Okay, and that's simply just looking at the stoichiometric ratio because there are 2 moles of carbon monoxide produced for every 1 mole of O2. So if we start with just carbon dioxide and then at the end we have 0.04 molar CO, we're going to have half that amount of O2. Now, there are 2 moles of carbon dioxide for every 2 moles of carbon monoxide. So that means that because there are 2 moles of CO produced for every 2 moles of CO2 that are consumed, that means that the number of moles of CO2 that are lost are going to be equal to the number of moles of CO that get created or produced in this reaction. And in this case, that is going to be equal to 0.040 moles per liter or molar. So we were asked not only for the O2 concentrations, but we were asked to find the CO2 concentration. And we know that we started with 0.250 molar carbon dioxide. So that means that the final carbon dioxide is going to be equal to what we started with, 0.250 molar, minus the amount that we lost, 0.040 molar. So the final concentration of carbon dioxide should be 0.210 molar. So we just did that using our stoichiometric knowledge. Okay, that's kind of not a new idea for us. There's a trick, though, to do these sorts of problems in a systematic manner. You can set them up using something called an ICE table, ICE table. So let me show you how to do that. I'm going to rewrite the reaction as 2CO2 going to 2CO plus oxygen. And then underneath the reaction, I'm going to make 3 rows and call them I, C, and E. Each of these rows is going to refer to a concentration. I stands for initial concentration, C stands for the change in concentration, and E, of course, stands for the equilibrium concentrations. And I'm going to record the concentrations of everything I know at the beginning of the problem. The only thing that I know is that I have 0.250 molar carbon dioxide. I'm not going to include the molar, but we know these are all concentrations in the table. It is implied, it's often implied in problems like this, that I don't have any products when I start out. So I'm going to put 0 molar for both of the products. The only other thing that I know from the problem, let's go back to the problem for a moment, is that I end up with 0.040 molar CO. So that's literally the only other thing that I know, that I have 0.040 molar CO. So what we just did a moment ago is we kind of used the stoichiometry of the reaction to fill in the blanks in this table. So to go from 0 to 0.04, I must have added 0.04. And because the stoichiometric ratio is such that I have 1 mole of oxygen for every 2 moles of CO that are produced, I'm going to be producing half the amount of oxygen for every mole of CO. So that's going to give me the equilibrium concentration of oxygen at 0.020 molar. Now, I know that the molar ratio of CO to CO2 is 1 to 1. And if I go to the opposite side of the reaction, I change the sign, right? I must be losing reactant to create product. So here I'm going to put minus 0.040. It's equal in magnitude but opposite in sign to the amount of CO. And the 0.25 minus 0.04 is going to give me the 0.210. So these in the last row, these are the molar concentrations of each of the species at equilibrium. So you can set up this ice chart to kind of help you organize the information in an equilibrium problem like this. Now, a particular ratio of equilibrium product and reactant concentrations is defined as the equilibrium constant, K. So we now are going to define the equilibrium constant, K. This goes back to the beginning of the lecture when I talked to you about the law of chemical equilibrium, which states that at a given temperature, a reaction reaches a state where the ratios of reactants and products is constant. A particular ratio of equilibrium product and reactant concentrations is defined as the equilibrium constant K, and this is just kind of a mathematical expression of the law of chemical equilibrium. In general, for the generic reaction, this is not a real reaction, I'm going to say AA plus BB is in equilibrium with CC and DD, where the uppercase letters are the chemical species and the lowercase letters are their stoichiometric coefficients. So for this generic reaction, I can define an equilibrium constant, uppercase K, where I take the concentrations of the products raised to the powers of their stoichiometric coefficients, okay, and that's a product, over the concentrations of the reactants raised to the powers of their stoichiometric coefficients, okay, the product of those concentrations. So everything in the brackets is a concentration. These square brackets are short for concentration. So everything within these brackets, everything that I'm kind of labeling in red here is concentrations. Whenever you see square brackets in chemistry, it means the concentration of whatever is inside those square brackets. All of these little exponents here, these lowercase letters, refer to the stoichiometric coefficients those big numbers in front of the reactants and products in the chemical reaction. So using this generic format, what would be the K, right? A K for the reaction that we just studied, where 2CO2 goes to 2CO plus O2. The K for this reaction would be the concentrations of the products, so CO, raised to the powers of their stoichiometric coefficients, so CO squared times O2 raised to the power of 1, over the concentration of the reactants, that's CO2, raised to the power of their stoichiometric coefficients, so that would be squared. Now, you can plug equilibrium concentrations, only equilibrium concentrations, into the expression for K. So you can plug equilibrium concentrations into K. And we calculated the equilibrium concentrations for this reaction in the example that we just did. We had 0.040 molar for CO, so that's going to be squared. 0.02 molar for oxygen, and 0.210 molar for carbon dioxide, and that has to be squared. So I'm plugging those equilibrium concentrations into the expression for K. And if I do that arithmetic, my K is equal to 7.2, keeping 2 digits of significance, times 10 to the minus 4 for that particular reaction that we just talked about. So this is an example of how to calculate an equilibrium constant. You need to figure out what the equilibrium concentrations are, write an expression for K, and then plug the equilibrium concentrations into K.